you ready? Are you ready? Oh, are you ready to go? Are you ready? Are you ready? Are you ready to go?
Hello, it's Mr. T, and today we have a tutorial on finding the derivatives of exponential functions. The rule for exponential functions is quite simple. The derivative of the function e to the x is itself. So the derivative is also e to the x. That means if we were graphing e to the x, which would have a y-intercept of 1, it would look like this kind of exponential function. If we are finding the tangent line at any point, let's say this point is x comma e to the x, the slope of this line is also e to the x. Frequently, the exponent on the exponential function will be some expression u. So using the chain rule, we can have a formula for the generalized exponential function where y is some constant times e to an expression. And when we find the derivative, it would still be k times e to that expression, but then we would have to multiply by the derivative of that expression. So again, we're using the chain rule here. So let's go through a couple examples of finding derivatives. So in this case, our u is 2x. So our derivative here, dy dx, will be e to the u times the derivative of u, which would be 2, or we would write that as 2e to the 2x. Our second example here, we have a constant in front, but that constant just gets carried through. So when we take the derivative, we now have 6e to the u times our derivative of the u, which would be 3x squared using the power rule. Now we could simplify. The 3 times the 16 is 18. Let's move the x squared to the front. And our third example on this page, our u is negative x, so dy dx is going to be e to the negative x times the derivative of our exponent, which would be negative 1. So we have negative e to the negative x. If we took the second derivative here, we would end up with e to the negative x. So each time we take the derivative, it toggles between positive and negative e to the negative x. Now this one will require, problem 1 here will require the product rule because we have an x in the front, not just a constant. So our u here is x and u prime is 1. Our v will be e to the x, and the derivative of that is also e to the x. So if we cross multiply for our derivative, we get x e to the x plus e to the x, and we could GCF factor out an e to the x, so we're going to have x plus 1 times e to the x. Now let's look here. Some of you might be thinking it's the quotient rule, but we could divide out. So we have 1/2 e to the x minus 1/2 e to the negative x. So we don't need a product rule or quotient rule. We just use our sum rule here. So the derivative of the first part is just 1/2 e to the x. And here we're going to have negative 1/2 e to the negative x, and then using the chain rule times negative 1. So this is going to become plus, and I could factor out the 1/2 again, and we're going to end up with e to the x plus e to the negative x over 2 for our derivative. Now we can apply the derivatives for finding relative extrema. We can also apply them for doing curve sketching. So let's try one of each of those. So in our example here, we have a business problem, and our demand for our product is given by this function here. P equals 56 e to the negative 0.000012x. So that's our price function, and we're trying to maximize revenue. So remember, revenue is price times x. So our revenue function would be 56x e to the negative point. There's 4 zeros here. Oops, another 0. So we need to use our product rule to find the derivative. So that's our u and our u prime. V is e to the negative 0.000012x. So v prime will be, when we do the chain rule, we're going to get that constant, so it's going to be that constant. And then e to that same exponent. So to get our marginal revenue, r prime, we're going to cross multiply. And here, minus 56x times. Now normally we would be wanting to multiply this constant here, but we're going to see here, since we have a 56 over here, we're going to be able to do some GCF factoring here to make this easier to solve. And that goes on x. So I'm going to factor out a 56 e to the negative 0.000012x, and our leftovers will be 1 minus 0.000012x. And we want to find our critical values to find our relative extremis, so we're going to set that equal to 0. Now, there is nothing that will make a exponential function equal to 0 so for this portion there is no solution. And over here, to get our critical values, we're going to set this equal to 0, a simple linear function, and if you solve that, you get x equals 83,333.3 repeating units. Now that would be the number of units of this product that we would want to sell to maximize our revenue, but our question asks for price, so we need to plug this back into our price function. And if we calculate that, we come up with a price of $20.60 as our optimal price. So it's just exactly like when we did these optimization problems in the before midterms, but now we have a new type of function that we can use. And our final example here will be a curve sketching example. If we plug 0 in for these x's to find our y-intercepts, I get 0 times 1, so we get 0, 0. If we set y equal to 0 here and solve, we would get 0 when I get here, so x squared would be 0, so we have the point 0, 0. And then if we set this factor equal to 0, there is no solution for that, so our only x-intercept is here. There are no vertical intercepts. There is nothing that will make this function undefined. Now, if we look at this as x squared over e to the x to look at, is there a horizontal asymptote? We can't quite use the rule that we have when we have a polynomial over polynomial. And we'll be talking about finding these horizontal asymptotes. But as x gets bigger and bigger, the value of x squared does get big quite rapidly, but e to a big number gets bigger even faster. So when this approaches infinity, the bottom number is going to approach infinity much faster than the top. So our horizontal asymptote is going to be y equals 0. We'll talk more about that in an upcoming lesson, but for now you can just take my word for that. Now we need to find our first derivative so that we can find our relative extrema. So again, our function here was x squared e to the negative x, so we have to use our product rule. And we know from earlier that our v prime then would be this. So if we cross multiply, our y prime is going to be x squared. Well, let's do it this way. So we have 2x e to the negative x plus our minus here, sorry. This is x minus, in this case, x squared e to the negative x, and we can factor out a e to the negative x. That's x squared, and that could be further factored into x times 2 minus x, and we want to set that equal to 0. Now there's nothing that makes that equal to 0. Here we get x equals 0 as a critical value, and here we get x equals 2. So on our first derivative number line, we've got 0 and 2. And again, we're going to plug that into y prime to find our increasing and decreasing. So if I plug a negative number, e to anything is positive, so we've got positive, negative, and then a negative number here is going to make that positive, so we're decreasing. Here I've got positive, 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 so we're increasing, and here I've got positive, positive, and negative, so we are decreasing. So we have a min at 0, 0, and a max at 2, comma, and this would be 2 squared, which is 4 e to the negative x, so e to the negative 2, which if we put that into a calculator is approximately 0.54. So if we go back up to the top, we have our increasing interval is between 0 and 2. And our decreasing interval is between negative infinity and 0, and then from 2 to infinity. And our min was 0, 0, and our max was at 2 and approximately 0.54. So let's look at our second derivative here for our concavity. So I'm going to use this version here to take my second derivative. So my u is going to be 2x minus x squared. So u prime is 2 minus 2x. V is e to the negative x, and v prime is negative e to the negative x. So when we cross multiply, we're going to be able to GCF factor out an e to the negative x, and when we go this way, I'm going to have 2 minus 2x, and here I've got negative times that, so I've got minus 2x plus x squared, or x squared minus 4x plus 2. So again, we want to find our critical values, so we're going to set that equal to 0 and that equal to 0. No solution here. To do this, we could use completing the square, or you could use the quadratic formula. So if we complete the square here, we take half of this number and square it, so we've got plus 4, and add that to both sides. This gives me x minus 2 quantity squared equals 2, and we square root both sides, and we get x equals 2 plus or minus the square root of 2, which if we evaluate that gives us approximately 0.59 and 3.41. If we put that on a number line and look at the second derivative, if I plug 0 into here, I've got positive. If I plug 1 into this, I end up with a negative number. And if I plug a big number in here for x, I get positive. So we're concave up, down, and up. So we have 2 inflection points here. So again, we are concave up from negative infinity to 0.59, and then again from 3.41 to infinity. We're concave down from 0.59 to 3.41, and we have inflection points at 0.59. And if I plug that back in up here to get my y value, I get about 0.19. And if I plug in the 3.41 up there, I get 0.38. So I'm going to let, for the x, every 2 here is going to be a 1. So that's 1, 2, 3, 4. And here, since our y values are small, I'm going to let 5 tick marks here be 1. So if we plot our points, we have a intercepts here, and that's also a min. And at 2.54, that's a half, so we're right around in here. We have a max. Remember, we have a horizontal asymptote coming out this way. And at 0.59, which would be around here, at about just around 0.2, we have an inflection point. And over here at just a little bit less than 3.5, we have an inflection point here at 0.4. And so over here we are concave up, so we're coming down here and going up. Between these 2 points we are concave down, and out here we're concave up and we're an asymptote, so it would look like that. So we can see here, this is our first graphing of a complicated exponential function. We were able to do that using the same curve sketching skills we used in Chapter 2. So good luck with exponential functions, and see you around.
Are you ready? Are you ready? Oh, are you ready to go? Are you ready? Are you ready? Are you